Now, entropy, which is represented by capital S, this is a measure of the randomness or disorder of a system. So we could say that if you increase the disorder of the system, you increase entropy. So really, entropy is really just kind of synonymous with disorder. What if you increase order of a system, then you decrease entropy? Now, if randomness, if disorder, if entropy increases, this is because the final entropy of your system is greater than the initial entropy of your system. And so final minus initial, which is your delta S, that's greater than 0. When we say that delta S is greater than 0, when we say that it's positive, we're saying that there's an increase in the disorder of the system, which we'll find later increases the spontaneity of a process and makes it more thermodynamically favorable. Now, entropy, it's disorder, but a way of describing that disorder is, or actually the origination of that disorder is it's the number of possible microstates of arrangement of your particles at a given moment. Entropy is proportional to this number of microstates of arrangement of particles. And so consider how these numbers of microstates are altered by a couple changes. Now first, consider that you're at 0 Kelvin. You're at absolute 0. There is absolutely no kinetic energy of your particles. They have no motion whatsoever. If you have a pure compound, all A here, then there's only one microstate possible. There's only this one possibility in which A is on top of A and on top of A, and they're all your particles are equally distributed about each other. There's equal distances between them. You have this one microstate, and here you have 0 entropy. Entropy is equal to 0 joules per Kelvin mole. But what if you increase the temperature? Well, now, having a higher temperature, you have a higher average kinetic energy of your particles. Your particles are moving about. And so now, you could say in the next moment, your particles will not probably be all equally distributed around each other. There might be greater distances between one particle than another. For example, this particle A right here, it might, in the next moment, be a little bit further to the right, further from this A. So there are varying distances between the particles, and so there's more possibilities for the arrangements of your particles. There's more microstates possible. And so we see that by increasing temperature, we increase the number of microstates, we increase the entropy of our particles. What if we add in some other compound into that batch of A? What if we add B? So we perhaps dissolve the particles together, and in this case, perhaps they're liquid. The particles are moving about significantly. There are varieties of not only possible distances between particles of A, but there are varieties of possible distances between A's and B's, and the numbers of B's near A's. This A is near 3 B's, whereas this A is near 2. There are more possibilities for arrangement. In the next moment, perhaps, this A might be near 2 B's, and this A may be near 0 B's. You can see that having this mixing, what you might expect in the next moment is more random. There's more randomness with how the particles might be arranged. So we can see that mixing increases the number of microstates possible and hence increases entropy. What if we turn our compounds into gas? Now they're moving much more than before because they have higher kinetic energy, and that's how gases are. The particles move much. And they're spread out more as well. And there are more possibilities for, again, the distances between the particles that they might have and what is near the particles. And so there's even a greater number of microstates, and there's greater entropy. So we can summarize all this in saying that mixing compounds increases entropy. Increasing the movement of your particles, particularly by increasing temperature, or by changing the states of the matter, increases entropy. And spreading your particles out increases entropy. So, These facts allow us to predict how a variety of changes affect entropy. So we could say dissolving compounds increases entropy, increasing their temperature increases entropy, and we'll get to these in a moment. Now, we mentioned that at 0 Kelvin, there is 0 amount of entropy because there's only one microstate if we have a pure compound. So 0 Kelvin, we have 0 entropy. What happens though if you increase the temperature? What if you take your pure compound and you increase the temperature? The entropy increases as well. That entropy increases as well. So we can see a positive slope there. Now, at some point, you're going to get to a point where you are at the freezing point or melting point, where even though the temperature is not changing, you can dramatically affect the entropy of your particles by changing the state. So if we had a certain compound, once we get to its melting point, we turn it from solid to liquid, and wow, its entropy jumps up dramatically. And then its entropy increases as you increase the temperature again until, boom, you get now to the boiling point, where you turn that liquid into gas, and boom, your entropy increases dramatically again. And then your entropy increases again as you increase temperature. We can see that there's dramatic changes in the entropy, not just by changes in temperature, but most especially by changes in state, from solid to liquid and liquid to gas. We can say that as you go from solid to liquid, you increase entropy, and as you go from liquid to gas, you increase entropy. The most dramatic change is with that liquid to gas transition. As you can see here, this is larger than this. Now, we mentioned that you can have more entropy by having mixing, but also having compounds bound to each other, or elements bound to each other, if they're different elements, can give quite a bit more entropy as well. So compare a CH4 versus C2H6. Now, which of these has greater entropy? So one reason you could say that C2H6 has greater entropy is just because it has more atoms. And generally, atoms and compounds have entropy. And if you have more atoms and compounds, then they have more entropy. But additionally, this has more entropy because there's more varieties of different positions of the particles around each other. There is continual rotation of compounds around a central atom. So for example, this hydrogen can move in this way or this way around that carbon. But also, these bonds can get shorter and longer. And additionally, this bond can get shorter and longer. And this can rotate about this carbon. You can see that the more bonds you have, the more possible rotations and vibrations you might have in a given moment, and hence the greater entropy that you'll have. This guy has more bonds than this guy, so he'll have more entropy. And then compare xenon to helium. Xenon is much larger. So xenon is big. Helium is small. Now on xenon you have electrons randomly distributed about, and they can have varieties of different distances between each other. And so just like atoms can have different positions around each other, electrons can as well, and so they also can contribute to entropy. So xenon has more electrons than helium. Helium has 2 electrons. Xenon has probably 80 or so. And so xenon has a lot more entropy than helium. The more electrons you have, the larger you are, the more entropy that you have. So oftentimes you'll need to predict how a reaction might affect the entropy. So is the change in entropy positive or negative for a given reaction? Now the biggest factor is the number of gas particles. If you increase the number of gas particles, you'll increase the entropy of all of your particles during that reaction. If you decrease the number of gas particles during that reaction, you'll decrease the entropy. You'll have a negative delta S. And if there's no change in the number of gas particles, then that change in entropy is probably going to be small or big. But it's going to be, I'm sorry, not small or big. It's going to be pretty small, positive or negative, but that value is going to be pretty close to zero, comparatively. So, a couple example problems. Here we have water going from liquid to gas. Well, you're turning a liquid to a gas, that is going to increase entropy. That's a positive delta S. Nitrogen combines with 3 hydrogens to give 2 ammonias. You went from having 4 gaseous particles into 2 gaseous particles. You lost gaseous particles, and so there's a decrease in entropy, negative delta S. Dissolve solid sodium chloride in water. Now the particles are mixed, and they're moving much faster as well. And instead of being solid, they're aqueous, basically like liquid. That's a dramatic increase in entropy. What about if you take 2 gaseous nitrogen monoxide particles and turn them into nitrogen gas and oxygen gas? Now, initially you had 2 gaseous particles, and later on you have 2 gaseous particles. There's no change in the number of gas particles. So there's not very much change in entropy. But what is going to be the exact change in entropy for this reaction? Well, you can calculate it using the following equation. The change in the entropy of a reaction, standard, so at 25 degrees Celsius, and at 1 atmosphere, is equal to the summation of the entropies of your products minus the summation of the standard entropies of your reactants. So sum all the products. In that reaction, it was N2 and O2 were the products. We had 1 of each, so we multiply them by 1. And then in reactants, we had 2 NOs, and so we're going to account for that. That 2 is coming from that coefficient there. Find the values in the back of your book or on the test. They'll be given to you. Sum up. Here, in this case, we got negative 68.7. Thanks for watching, guys.